Okay, folks, thank you very much for your efforts so far, and thank you very much to whichever cover teacher is in there with you today. We're going to go through Sankey diagrams. Now, hopefully this isn't going to be as tricky as I think it's going to be, but just keep listening, and if you get confused, just rewind the video. Ask the teachers to rewind the video or to pause the video and then to go through the explanations again. We should have done these in Key Stage 3, so this is just a bit of a reminder. For now, though, can we find somewhere, either on the envelope or on a piece of paper that you've got in a previous lesson, to just try and answer these questions up on the board? Thank you very much. Get as many of them as you can done in the next 5 minutes, and then whoever is with you is going to give you an opportunity to mark your work with a red and green pen. So if we could pause this for about 5 minutes. All right, lovely. Just in case there was massive confusion there, I'm just going to nip through it. Describe the energy stored changes when a rocket firework is lit, goes up in the air, and then falls back in the ground. You should have remembered that energy stored changes are these movements from one box of energy into another box of energy. And all three of these questions are just asking you to, with words, say, what was the first energy store, what was the transfer, and what was the next energy store? So hopefully we managed that. If nobody managed that, or if it was incredibly difficult, then why don't we just take, you can pause now again if needs be, to let people see that. Otherwise, here are your answers. So chemical energy that's in the fuel is transferred to kinetic energy by heating and forces. So that's when the firework goes up. Kinetic energy turns into gravitational potential energy by forces. So this is, as it's moving up as well, and it's turning into gravitational potential energy. So the kinetic energy of that fuel, the kinetic energy of that rocket, pardon me, is going up, pushing the rocket up to make it get gravitational potential energy. This gravitational potential energy will eventually be turned into kinetic energy as it starts to fall. So it's going to go up and then fall back down again. And as it's going that back down again, all the GPE is turning into kinetic energy by forces. This force was gravity. And then finally, kinetic energy will be converted into elastic potential by forces when the rocket hits the ground. When a cyclist is braking hard to avoid a collision, describe the energy stored changes as the bicycle and rider decelerate to a stop. Kinetic energy will be turned into thermal energy by friction forces in the brakes. When a battery stops working, people often say that energy has been used up. Explain why this statement is not correct. Because energy cannot be created or destroyed, it can only be transferred to another store. So the energy hasn't been used, it has just been transferred. Okay, so we're going to be looking at some Sankey diagrams today. Now I'm going to give you a brief reminder about what they look like. So it is an arrow wherein there is a bottom part and there is a top part. Now, we can draw Sankey diagrams which show the amount of energy that's being used by different objects. So if we were to take something like a light bulb, it's a common example of a question that we might get. So the Sankey diagram shows us the energy transfers that are happening, and it also shows us the useful energy transfers as compared to the wasted energy transfers. So this all ties in with what we've been learning in previous lessons about efficiency. Right, in a Sankey diagram, you will have an area over here, which is where the total energy is represented. So the total energy is shown by the width of the arrow. So we'll say that's 100 joules. Now, much like when you go to sit on a toilet and you want to get rid of any waste, the waste goes down into the bottom of the toilet. I'm going to label that just because I don't know if I'm very good at drawing or not. The waste goes downwards. So when you take a number 2, it goes down your loo. The same thing happens in a Sankey diagram. When an arrow goes down, it shows the waste energy or the energy that isn't being used properly. Now here it's not drawn to scale, but I might say that that's 20 joules of energy. And I can also tell the amount of that by the width of the arrow. Now we can clearly see that there's more energy that's being used in this arrow. This arrow is a lot wider than the previous one. Now the energy that goes across the top of the Sankey diagram is the useful energy. So in this particular example, there's more useful energy than wasted energy, so it's going to be quite an efficient light bulb. We like that. We can also figure out the total amount of useful energy. If 100 joules is the total amount of energy and 20 joules was the amount that was wasted, and if the amount of energy into the system is equal to the amount of energy, energy out, then I know that this number here has to be the remainder of those two numbers. So 100 joule goes in, 20 gets used as waste. How much is left over to be used as useful? And you guessed it right, 80 joules. So what are the rules when it comes to drawing Sankey diagrams? Well, the first thing is that it's the width that's important. That you need to make sure the width of the arrows shows how much energy there is. So either the total width, the useful width, or the wasted width. Number two, it has to be to scale. Now, a scale just means that if I say that 1 centimeter is equal to 1 joule, then I make sure that if I am drawing this arrow, that I make it 100 centimeters across. Why would I make this arrow 100 centimeters in width? Because it's 100 joules. If 1 centimeter equals 1 joule, and I want to represent 100 joules, then I will have to draw 100 centimeters. What would the width be of this arrow if 1 centimeter is equal to 1 joule? You guessed it, it's 20 centimeters. And well, what would the width of this arrow be if it was 80 joules of useful energy? This arrow would have to be 80 joules wide, which is 80 centimeters wide. The third is the order that you draw things. Now, if you draw them in the correct order, then it means that you are going to have a more successful drawing. So we always start off with the total, then we draw the waste, then we continue on our useful top line, useful line top, then we draw our, this is going to make more sense in a minute, our R, and then finally we finish our useful. Okay, now I'm going to be doing the Sankey diagrams that are on your sheet in front of you. They are not going to be very good. I'm going to try my best, but I'm using a mouse to draw, which means that my drawings aren't going to be very good. Everyone in that room must use a pencil and must use a ruler. Absolute must. If you don't have a pencil and a ruler, then well, I'm very disappointed. All right. This will be the extension if we get the rest of the task done. There is some graph paper in the room there for you to use. And here are the list of things that you have to do and able to do the Sankey diagrams that I've asked you to do. But for, oh, hang on now, what's going on here? But for now, we're just going to crack on with the ones that I want you to draw, which is here. So this will be on the sheet in front of you. I'm drawing this in Microsoft Whiteboard, so it's not as good as it could be, just because they've updated the system software, making it harder, which is, you know, what you want to hear, isn't it? So let me get this started. Oops. Okay. 700 joules of electrical energy is put into a remote control car, which is converted into 200 joules of kinetic energy, and the rest becomes heat and sound. Well, the first thing I'm going to do, because I'm a good scientist, is I'm going to write down that the total energy, and you're going to copy along with me. This is a model that we're doing together. So everything I write on the board here, you write along with me. I'm going to write down that the total is equal to 700 joules. If at any point you need to pause, just ask cover teacher to pause. 700 joules of electric energy is put into a remote control car, which is converted into 200 joules of kinetic energy. Well, I want my remote control car to move, so it sounds like that useful energy is going to be the kinetic energy. Useful energy equals 200 joules. The rest becomes heat and sound. So I can combine together the heat and sound, and that will give me my wasted energy. My waste is equal to 500 joules. All right, now I've identified the different types of energy, the different lines I'm going to have to draw. So it's the width of the lines that matter. So when I'm thinking about drawing this, I don't want to be worried about having a longer arrow or a shorter arrow. I just want to think about the width of these different arrows. I'm going to sketch out what it would look like, probably something like that, with 500 down there and 200 up there. So I'm just going to, there we go. And it's going to look something like this. Now I want to make sure that I can get my 700 joules and an arrow for my width down here. So I can't just say that this is equal to 700 joules. That's not going to work for us, because where would the arrow go? Where would my scaled arrow go? So we can't do that. What I am going to do is I'm going to start in this top little corner here and then see what scale would work the best. Because the scale is important. Remember, I'm going to have to make sure that a certain number of squares or a certain number of centimeters is equal to a certain number of joules. Now, I could say that 1 square is equal to 700 joules, which is going to be a very, very small Sankey diagram, and it'll be difficult for me to do all the other bits to scale. So we're not going to do that. I could say that 1 square is equal to 100 joules, which would probably work. And I'm just going to sketch this out, so I don't want you to draw this, okay? So purple pen means don't draw it. 1, 2, 3, 4, 5, 6, 7. Actually, I just realized there that you'll have been drawing some stuff in your Sankey diagram. Okay, so if it's in purple, don't draw it. Sorry, folks. I am learning how to do this as we go along. 1, 2, 3, 4, 5, 6, 7. So that's the 7 that it goes down. I'm going to sketch that across. I'm going to move this across, and I'm going to do a 1, 2, 3. Yeah, okay. So basically, it's a very small diagram. And I don't like the very small diagram that I've got in front of me, so I'm not going to say that. That isn't going to be the number that I choose after all. Going back to red now, so I'd like you to copy down after me. I am sorry for that confusion. It won't happen again. Let's say that 1 square is equal to 50 joules. 1 square by itself will equal 50 joules, and that means that I'll be able to draw a fairly big diagram, but there will still be a little bit of room left over. I'm going to start up here, and if 1 square equals 50 joules, I'll have to go down 14 squares. Now, what I'm going to ask you to do is literally count. So go 1 square, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There is the first line that you have to draw. From this first point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 points away. You're going to pick up your ruler and you are going to draw your first line. You are not to do what I am doing. Do as I say, not as I do. What I've done there is I have done my total line. That is how wide my arrows are going to have to be. Now what I have to do is start drawing the arrow. I'd go across 3 or 4 blocks. In this case, we're going to go across 4 blocks so that we've got the beginning of an arrow. Now I need to do which one, my useful or my waste energy. I'm going to be doing my my down arrow now, my waste arrow. So which one am I going to be doing? Am I going to be drawing the arrow up here at point A or down here at point B? I'm going to be doing the one down at point B. And I need to make 500 joules of waste. So 500 joules of waste is going to be 10 boxes of 50 joules. This is my scale. So I'm going to start counting again. I'm going to start here. And I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots across. And I'm going to draw another dot there, a big one that I can see. This is going to be the width of my waste arrow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots across. And again, I'm going to push this arrow down. So I'm going to draw the arrow. I'm going to go down about 4 boxes. And then I want to make the tip of the arrow. Now, I've got 10 boxes here. Halfway through 10 is 5, so I'm going to count 1, 2, 3, 4, 5, and then I'm going to go down a couple of boxes, and I'm going to draw a point. So I'm going to count half the number of boxes that are there. I'm going to go down a little bit, and I'm going to draw another point, and that's where I can connect the tip of my arrow. Next part, so I've done my waist, I've done my width of my waist, and I've done my arrow. Next part then is I'm going to do my useful top line. And all that means is I'm going to carry this line on past my waist arrow. So here's my waist arrow. I'm going to carry that line on past it. Then I'm going to have to do my useful width. Now, 200 joules in 50 joule increments is going to be 4 boxes. So if 1 box equals 50, 2 boxes, 100, 3 boxes, 150, 4 blocks is 200. So I'm going to put a dot there. And I'm going to count down 4 blocks. 1, 2, 3, 4. 1, 2, 3, 4. That is the width of my useful arrow. Now, this is the only tricky part of drawing a Sankey diagram. It's this awkward little corner that we have to do. Now, this is the reason why you're going to be using a pencil and a ruler. Now, unfortunately, I can't actually do this, but what you would do is you would draw a line, not all the way across, but a bit of the way across, to join up your useful width. And then you were going to draw an arrow up from up from the wasted arrow until they intersect. You then get your rubber, and my two lines are going to disappear unless I can change. Oh, hang on. Okay, let me have a look. Yeah, okay. And then all you have to do is rub out those extra lines that we did. And I'll show you that again, just because it is a tricky part for some of us, especially me, apparently. Oopsie. So I'm going to draw my useful line down. I'm going to draw my wasted line up. And then I'm going to get rid of any of these bits of line that are moving into the Sankey diagram. Then all I have to do is finish off this arrow. So again, I'm going to count. I've got 4 boxes here. I'm going to count halfway in. 1, 2. I'm going to go down 2, draw a point, and that is how I connect my arrows. Now I need to label. So I'm going to write down here that this is 700 joules of electrical energy. Now it should be electrical transfers, remember, because there's no such thing as an electrical energy store, but I just left out the word electrical energy transfer there. I'm going to write down that there is 500 joules of heat and sound. And remember, sound is also a transfer, but in this case, we can say that it's transferring energy away from my remote control car. And then this is 200 joules of kinetic energy. That's the next bit, and it's the last one, step 4. Well, not really, but you know what I mean. Labeling. Now, if needs be, you can record. You can rewind this to have a look at how I did it and to make sure that you know exactly how you're doing it. But just remember, it's the width that the scale is important to make it not too small and not and just big enough so that you can see a nice Sankey diagram. And to make sure that you read the question to make sure you know what is useful and what is waste. Now, those who feel confident can crack on to the next one. I am going to spend just a couple of minutes very quickly drawing the next Sankey diagram as an idea about what you can expect. If you'd like to, you can pause now and show this up on the board until everyone is finished taking it down. Okay. I'm just going to see if I can do something clever here while we're waiting. Did that work? Hey, look at that. Very clever. Oopsie. Okay, hang on. Okay, not as successful as I thought. Okay, hang on. I can do this. Okay, no, can we just undo all that? Right, okay, don't worry about it. Okay, so a light bulb takes in 100 joules of energy and gives out 25 joules of heat and 75 joules of light. I am going to say that if you want to, you can do that. One box is 5 joules, and that means we'll have to go down 20. Or we can say that one box is 10 joules, and we're going to have to go down 10, then 2.5, 7.5. Yeah. Okay, so for this one, I'm going to say that one box is 10 joules. Just because I don't know if I'll be able to draw a long enough line. So, light bulb takes 100 joules of energy and gives out 25 joules of heat. So we'll say that total energy is 100 joules. We'll say that the wasted energy is 25 joules and that the useful energy is 75 joules, because we obviously want my light bulb to be giving out light. So if one box is 10 joules, then I'm going to draw down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I'm going to connect that up. That's my total line done. Then I'm going to draw across 2 or 3 boxes. Now I need to do my wasted energy, which is going to be the 25 joules of heat. So I'm going to start here. I'm going to count 1, 2, and a half. and I'm going to draw my dot there. And I'm going to go down 1 or 2, down 3 or 4, and I'm going to count about halfway in and go down 2 dots, which will be about there. That's about 1.625, and there we go. I've now drawn my waist arrow. Next step, I'm going to carry on my useful line until it goes past this waistline, and then I'm going to see what the width of that I would like it to be. The useful is 75 joules, so I'm going to count down 1, 2, 3, 4, 5, 6, 7.5. And I'm going to draw my line in there. Ooh, okay. I'm going to count about 3.5, so it's I'm going to count down 1, 2, 3.5, and then a little half. I'll go down 1 or 2 lines there, and I will connect my arrow. And I do my awkward R. And I label it. This is quite a small one, so I shall say 25 joules of heat. So I can draw an arrow for that. I can draw a label for it, pardon me. And then I can say 75 joules of light. Okay, so you should have gotten something like that. Again, you can mark in red and green pen. And I'd like you to try and do the next one without any help from myself at all. So if teacher could just pause this video and then skip forward until where you see the next Sankey diagram has been drawn, that would be fantastic. The answer, and then it'll just pop up on the board for the kids. All right, thank you. You can pause. I'm going to keep recording while I draw this, though. If anyone is massively struggling, let them have a look at this if needs be. So it takes in 10 joules. I should leave it up to your discretion, because I have absolutely no idea how well this is going down in classroom. It's really scary, actually. All right, 3 joules of heat in a light bulb. That's going to be wasted energy. And if the total amount of energy going in is equal to the total amount of energy going out, then the total energy, pardon me, silly Billy, useful energy will equal 7 joules. I'm going to count down, I'm going to make my scale. I'm going to say that 1 box is equal to 1 joule. I'm going to count down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 dots, add my line, go in 2 or 3. Do my dot. Wasted energy is 3 joules. 1, 2, 3. Do my next dot. Write my line down a little bit. Halfway between those 2. Carry on my useful line until it goes past my wasted line. It's going to be 7 of useful energy. Draw my dot. 1, 2, 3, 4, 5, 6, 7. Here's my dot. I carry my useful line all the way back. I'm going to draw my arrow to about halfway between those 2 points. Drop up from waist. Label it. And because there's no specific energy given, then I'm just going to say total energy. I can say 3 joules of heat. And I can say 7 joules of light energy. Okay, that's us done. I think that was all it was, wasn't it? Oopsie. So frustrating. All right. Okay, so we can just skip in here now. Here's the final answer. Now, if anybody has any questions, then please do let me know. And if we have finished that, you can go on to the extension that's on the screen, or will be on the screen, pardon me, in just a minute. If you just pause and let the students mark that piece of work. And if teacher could then, first off, have a go of, no, first off, have a go of these. If they've finished all the drawings, then these 2 questions should be at the bottom. So it's just a hand sketch. I don't want anything to scale. I just want it rough. Just vaguely looking as it is in the picture. So here's the answer for these. So we just pause and let the students do that. And here are the answers. So you can see that even though the energy efficient light bulb gets 10 joules of light, so does the filament light bulb. The filament light bulb wastes so much more energy compared to the energy efficient light bulb. And here is the extension. So here are 2 more Sankey diagrams that you can do. And I shall leave that up on the screen for you. Thank you very much for whoever is covering my lesson. If there's any confusion, I promise I'll wrap it up when I get back into work. If there's any questions you have, then please email me and I shall get back to you as soon as I possibly can. Right, thank you very much.